Today, we delve into the intriguing story of Stephen Hawking's bold wish to create black holes here on Earth. The incredible physicist visited the renowned Large Hadron Collider, hoping for a groundbreaking physics discovery. It turns out that his dreams might not be as far-fetched as they seem. As we ventured deep underground into the 5-story cavern housing the ATLAS experiment at the CERN lab near Geneva, the atmosphere was filled with anticipation. It was the year 2009, and a lawsuit had been filed in the United States, expressing concerns that the newly constructed Large Hadron Collider could potentially generate black holes or other dangerous phenomena. The LHC, a massive ring-shaped particle accelerator, was primarily designed to unravel the mystery of Higgs bosons, the missing piece of the standard model of particle physics at that time. Hidden beneath the Swiss-French border, this colossal machine boasts a circumference of 27 kilometers, almost 17 miles. It accelerates protons and antiprotons in opposing beams to an astonishing 99.99% of the speed of light within its circular vacuum tubes. At 3 specific locations along the ring, these accelerated particles collide with immense energy, simulating conditions similar to those just moments after the Big Bang when the temperature exceeded 1 billion degrees. The collision results in a spray of particles, which are captured by millions of sensors meticulously arranged like Lego blocks to create colossal detectors, such as the ATLAS detector and the Compact Mons Solenoid, CMS. Fortunately, the lawsuit was eventually dismissed, acknowledging that speculative fears of future harm lacked sufficient grounds. In November of that year, the LHC was successfully activated, following an earlier explosion mishap. And to the excitement of the scientific community, the ATLAS and CMS detectors soon detected traces of the elusive Higgs bosons amidst the debris of the particle collisions. However, as of yet, the LHC has not produced any black holes. But here's the thing, Stephen Hawking's hope for black hole creation at the LHC wasn't entirely unfounded. We often think of black holes as remnants of collapsed massive stars. However, this view is rather limited, as anything can transform into a black hole when compressed into a sufficiently small volume. Even a single pair of accelerated protons and antiprotons, colliding at nearly the speed of light within a powerful particle accelerator, could give birth to a black hole if the collision concentrated enough energy into a tiny enough space. It would undoubtedly be a minuscule black hole with a fleeting existence, as it would evaporate instantaneously through the emission of Hawking radiation. Now, imagine if Stephen and the director of CERN, Rolf Hoyer, had achieved their wish to create black holes. It would have signaled the culmination of decades of research by particle physicists to explore nature at increasingly smaller scales by colliding particles with ever higher energies. Particle colliders serve as microscopes in the world of physics, but gravity imposes a fundamental limit on their resolution. Whenever we attempt to delve into smaller volumes by increasing energy, gravity triggers the formation of black holes. Interestingly, at this point, adding more energy would only generate larger black holes instead of further enhancing the magnifying power of the collider. This peculiar behavior challenges the conventional thinking that higher energies lead to the exploration of shorter distances. Instead, it suggests that the construction of larger accelerators doesn't ultimately lead us to a fundamental smallest building block, the cherished dream of every reductionist. Rather, it points toward the emergence of macroscopic, curved spacetime. Gravity mocks the notion that physical reality is neatly organized into nested scales that we can peel off one by one to reach the tiniest constituents. Gravity, and by extension, spacetime itself, possesses an anti-reductionist element. So, at what microscopic scale does particle physics, devoid of gravity's influence, transition into particle physics intertwined with gravity? Or, to put it differently, how much would it cost to fulfill Stephen's dream of producing black holes? This question lies at the heart of the unification of all forces. The pursuit of a unified framework encompassing all the fundamental laws of nature was a dream that began with Einstein. It directly relates to whether multiverse cosmology can offer an alternative perspective on the life-enabling design of our universe. Only by understanding how particles and forces harmoniously fit together can we gain deeper insights into the uniqueness, or lack thereof, of the fundamental physical laws and the extent of their variability across the multiverse. That wraps up this captivating story of Stephen Hawking's quest for black holes and the intriguing interplay between particle physics and gravity. Make sure to subscribe to our channel for more mind-expanding scientific adventures.